In today's lesson, we're going to review Chapter 5-6, which is a review of radicals. So if you recall, whenever you have a radical, the number inside the radical right here is called the index. The actual number that is inside this radical here is called the radicand. So to review, for example, if we wanted to take the square root of 9, we want to know, because this index is a 2, what two numbers multiply to 9? Well, those two numbers can be 3 times 3 or negative 3 times negative 3. So the square root of 9 is actually a positive or a negative 3 as your answer, because I can do 3 times 3 and get 9, or negative 3 times negative 3 and get 9. If I do the cubed root of 64, I want to know what number 3 times, because my index is a 3, gives me 64. Well, the only number 3 times itself would be 4 times 4 times 4, so my answer is just 4. So 4 3 times is 64. On this next example, we're going to do the fourth root of 16. So again, I want to know what number 4 times is going to give me 16. So I can do 2 times 2 times 2 times 2. Or I can actually multiply negative 2 times negative 2 times negative 2 times negative 2 and still get a positive 16. So the answer to this one is a positive or a negative 2. So notice that when my indexes are even, for example, there's a 2 here and a 4 here, I'm getting two answers, the positive and the negative one. When it's odd, I'm just getting the 1. So that's what we're going to fill in first for the number of real roots. So if we have odd indexes, you're going to have one real root. Let me erase that. If we have even indexes, then we need to look at the number inside here. If the number inside is positive, and remember that number is called a radicand, so if we have a positive radicand, we're going to have two real roots. If we have an even index, but the radicand is negative in here, remember when you do the square root of a negative number, it comes out as an I. I is imaginary, which is not real. So when my radicand is negative, then I'm going to have 0 real roots. So we're going to use the properties to simplify some radicals. First example, if I wanted to do the cubed root of 16, and I want to simplify this, well, 16 is not a perfect cube. There's no 3 numbers that are the same that multiply to 16, but I can still simplify this. One technique is to break it down into the prime numbers. So 16 breaks down to 4 times 4, and each 4 breaks down to 2 times 2. So I can rewrite this as 2 times 2 times 2 times 2. So this index tells me this is how many I need in a group in order to take it out. So I actually need 3 2's to take out a 2. Well, here's 3 2's. So that means I can take this out as a 2, but then I'm left with still a 2 on the inside. Now this is simplified. Another way of looking at it is you want to find what number that is a perfect cube that goes into 16. So you could separate and do the cubed root of 8 times the cubed root of 2. 8 is a perfect cube. 8 times 2 then is 16. So this number here is a perfect cube of 2 times the cubed root of 2, which is the exact same answer that we just wrote. So either method is appropriate. So on this one, I'm going to do the fourth root of 16x to the 8th over 5. I like to separate this as two radicals. The numerator over the denominator. So same idea applies. I need to know what number 4 times is 16 if something exists. And then I need to see how many groups of 4 I can make out of 8 x's. Since we're learning this in here for the first time, even though it is a review of some Algebra 1, I'm going to go ahead and break 16 down to the prime numbers and x down too, so you can see the breakdown of where these groups are coming from. So 16 is 2 times 2 times 2 times 2, as we see up here. And then I have 8 x's. This is telling me that I need 4 in a group in order to take it out. So there is 4 2's, here's 4 x's, and here's 4 x's. So I can actually take out a 2, an x, and an x. Well, 2x times x is 2x squared. So my numerator now is 2x squared. My denominator is the fourth root of 5. This is a prime number, so it doesn't break down anymore. So we're going to keep it like this just for a second. Now that once we're here, one of the rules of radicals is that you can never keep a radical in the denominator. So we need to get rid of it. In order to get rid of it, it's called rationalizing the denominator. So I need to multiply by something that is going to cancel this index out. Well, the only thing that will cancel this index is if I have 4 5's on the bottom. So 4 5's will cancel this. So I already have 1, which means I need 3 more. 1, 2, 3. So together now I have 4. Whatever you do on the bottom, you have to repeat on the top. So on the top now, the numerator, I have 2x squared times the fourth root. And let's go ahead and multiply this out. This is not going to simplify it all because I only have 3 5's and I would need 4 of something to cancel. So we're just going to keep it as the fourth root of 125. Since it's in the numerator, it's okay to have a radical left over. You just can't have one in the denominator. Now on the bottom, if you look, I have 4 5's. So that means I can take out a group of 4, and this number down here becomes a 5. So your final answer is 2x squared times the fourth root of 125 all over the number 5. Another thing we're going to review is rational exponents. Rational exponents are exponents that are written as fractions. And we're going to use m over n to represent our fraction. So rational exponents can be rewritten as a radical. So any variable or number to the m over n is actually equal to the nth root, so the denominator becomes the index, of x to the m power, or you can write the power on the outside of the radical like this. So either one of these is appropriate. So for example, if I wanted to rewrite 81 to the 1/4, then the denominator of the fraction, which is a 4, becomes my index, and then I can do 81 to the first power. It doesn't matter if I put the first power here or out here on the outside. I'll just put it on the inside on this problem because anything to the first power is not going to change this problem. So to simplify it, I want to know what number 4 times is going to give me 81. So let's go ahead and break down 81 into the prime numbers that make it up. So 81 is 9 times 9, and then each 9 becomes 3 times 3. So 3 times 3 times 3 times 3. So as you can see, 81 is a perfect 4th root because there are 4 3's, and that matches the number that is on the index. So my answer is 3. If we had 16 to the 3/4 and I wanted to simplify this, so again I'm going to use the denominator of the fraction as my index, and then I'm going to do 16 inside here, but I'm going to choose to write the exponent on the outside. If I put it here on the inside and I calculate 16 to the 3rd power, that's a really big number and I don't want to mess with that. So I'm going to do this piece first and then raise it to the 3rd power. So I want to know 16, what does that break down to? Using prime numbers. Well, 16 is 4 and 4, and 4 is 2 times 2. So I'm going to get this value and then I'm going to cube it. So notice that this tells me I need a group of 4. Well, here is a group of 4 2's. So this answer is 2, and then I need to cube that. So 2 times 2 times 2 is 8. Now we're going to rewrite them. We're going to start as radicals and rewrite them as rational exponents. So if I had the 5th root of 2 cubed, if I rewrite this, I have 2. Now remember, this power here is your numerator and the index is your denominator. So 2 to the 3/5. If I had the 5th root of 2 to the 10th, again, the power inside here is my numerator, the index is my denominator. But if you look, 10 divided by 2, I can simplify this. I can't simplify 3 over 5 any farther. That's why this answer was finished. So this becomes 2 to the 2nd, which we can work out to be the number 4. Lastly, we're going to review the properties of exponents. So the first property is if you have the same base and you're multiplying, try to think, what do you do with these exponents? If you said that you add them, you are correct. If I have the same base and I'm dividing these, try to think back of what you would do with these two exponents. If you said subtract them, you are correct. The third property is when you have an exponent raised to another exponent. So we have an exponent to an exponent. And the property when you have an exponent raised to another one is that you will multiply those exponents together. The last property is if you have two bases raised